Hi, and welcome to our presentation of the Controllable Active Search Collection Robot, the CatBot, a light-guided trash collection robot. I'm Braden.
I'm Griffin.
I'm Kobe.
And I'm Adam.
So for the motivation and background of this project, it is very difficult for physically disabled or elderly people to bend over and crouch down and pick up things off the floor. And while there are other autonomous robots out there, they're only capable of picking up very small pieces of trash and dirt off the floor. CatBot acts as a trash collector that can pick up some of these more larger pieces that some of these other autonomous vacuums may not be able to pick up. So for our goals and objectives, for our basic goals, we have that the robot can traverse the room. It does this using wheels, stepper motors controlled by an MCU. The robot will also uses visual cues from a laser pointer to identify trash and move toward it. And the robot uses optics to avoid obstacles using an IR LED. For our advanced goals, the robot picks up objects off the ground utilizing our arm servo system, and the robot maps the room using SLAM, using a LiDAR sensor. So for some of our stretch goals, the robot will be able to differentiate between trash and recycling using some sort of artificial intelligence or image recognition. And our last stretch goal is that the robot will not require any sort of human physical interaction or maintenance during operation.
So this is a overall schematic of our optical schematic diagram. As you can see here, you've got the IR laser, which inevitably actually ended up being on the right of this setup, over the camera, and over the LiDAR system at the very bottom there. So what we're doing is we're taking a modulated red laser array to point at different objects in our environment that the robot can also see with its camera, which is finely tuned using filters for our specific red wavelengths to see that light. We're finding objects in our environment and we're picking them up with the arms. The tune lens system of the laser is perfectly tuned to be 50 degrees, with an up tilt of 25 degrees on the drivetrain, in order to accurately sort of find which objects in the environment are too tall to be picked up. So that's an overview of our optical subsystem and schematic. Next is our engineering requirement specifications. So the system must be able to pick up trash within 20 feet within a specified time of 2 minutes or 120 seconds. The arms attached to the servos should be able to pick up objects up to a specified weight of 2 pounds. And the red laser in the remote must modulate at a frequency detectable to the wide field of view camera, but not the user. So that's about 50 hertz or 100 frames per second. Here's all of our component specifications as well. So we have our chassis, which is a maximum weight of 8 pounds. Our servos and arm, which are a maximum object weight of 2 pounds. And the camera, which is field of view, is 66 degrees. Here's our hardware block diagram as well, which shows more optical connections like the IR LED transmitter at 940 nanometers, modulated at 38 kilohertz, going into the IR receiver, which is finely tuned to that 38 kilohertz to be received. For our button presses on our remote, but also our red laser array, which is also on our remote, going and highlighting, all trash in the environment. Our tall trash as well is going to be highlighted by our IR laser, which is coming from the chassis on our robot. That would be tall trash. And then the LiDAR as well is going to be selecting at 905 nanometers any object in our environment. It's going to take a swipe so that it can see its environment. All of that goes into our processing system and our motors in order to tell them what to do. Our optical design calculations are also important. Here's our red laser array PCB design, which was modulated at, again, 50 hertz by the timer circuit equation for the frequency. It's a ratio of resistors and capacitors. Next one. So here's another one. Our IR LED PCB design is, again, using the same formula, but we modulate both of those timer circuits inside of a BJT transistor to bias our IR LED. The IR LED also has certain calculations and specifications for intensity. Here we're just calculating the optical power which turns out to be 8 milliwatts for the laser that we selected, or the LED we selected, sorry. That's what we modulate with the 555 timers in the previous slide. Also our IR receiver calculations and specifications. And our IR laser calculation and specifications. So our IR laser is a CREOL 808 nanometer IR laser with a beam waist size of 1.5 millimeters. These equations below derived from the ABCD matrices were calculated in order to assure the beam divergence exiting the chassis is at exactly 50 degrees, creating a beam parallel to the floor for height measuring of pieces of potential trash in the environment. Now our comparison of hardware and software.
So for our single board computer, we looked at 4 different main ones. We looked at the Raspberry Pi 4B, the NVIDIA Jetson Nano, the Latte Panda Delta, and the BeagleBone AI64. And we ultimately landed on the Raspberry Pi 4B, mainly due to its good price, as well as other competing specs that are listed below. Next, for our MCU, we chose between the ESP32, Arduino Nano, MSP430, STM32 family, and the Raspberry Pi Pico, and we ultimately landed on the ESP32 mainly because of its high performance compared to the other microcontroller families.
In addition, the ESP32 can be programmed using the ESP IDF Integrated Development Environment, which was very helpful for developing firmware for this robot.
So for our operating system and ROS selection, we decided to go with the pairing of Ubuntu 24.04 as well as Jazzy Jalisco. Ubuntu 24.04 is the latest long-term support release of Ubuntu, and we figured pairing that with a Tier 1 support system that goes along with Jazzy Jalisco, we just figured that this would be the most, the best configuration for our robot.
To program our robot, we decided on using both Python and C to program the different parts of our robot. For the ESP32, we used embedded C using the ESP IDF development environment, which was really helpful as it provided the ability to create reusable components for our robot and create a modular system. Python was also used for developing code on the Raspberry Pi as ROS nodes, which was also modular and made it very easy to have different subsystems communicate between themselves. To map SLAM, which is simultaneous location and mapping, we used SLAM Toolbox as it is the de facto SLAM library for ROS2.
Our first decision to make regarding the design of our robot was the chassis. It was decided to start with a kit that would serve as a skeletal frame to build our design on. We considered a few different chassis, and we finally decided on the Professional Smart. It was selected due to its lightweight aluminum construction and its bare-bones I-frame design. The 12-volt DC motors that it came with also proved more than adequate for testing the locomotion of the design. We considered some others, such as the Lewin Soul, but the platform was just too small, and most of the other ones were too expensive, as you can see on the Yaboom robot. After we completed the prototype of the robot, it was decided to switch to a stepper motor design, the NEVA 23 enclosure size, because of the 20 amps of stall current that came with the initial DC motors. This was deemed too unsafe not only for our components but also for people, as the inrush of current on startup would be too much and would probably cause flyback problems.
So then our camera selection as well. So we chose the Raspberry Pi near infrared camera version 3. It ran at 66 degrees of freedom angularly to see the field of view. It has infrared capabilities as well as autofocus, dynamic range. At our desired frame rate, it runs at like 720p at 100 FPS which is what we're going to modulate our red laser array to be. Along with having desirable other things, it was very low price compared to the IDS imaging U3. It just seemed like the best option for us, considering all of our different costs. Additionally, our laser selection. So here you can see sort of a snapshot of our midterm demo where we did a red laser array on top of our IR laser, which had a sort of quirky design flaw, which we ended up kind of moving away from for illumination, which is the line streaking that happened on that laser particularly. But that's the Kyoba infrared 808 nanometer. We chose these two lasers for their affordability and also the fact that they are also consumer safe at less than 5 milliwatts. We also selected very carefully our filters to put in front of the near infrared camera. We ended up going with this long pass filter, which is dielectric, with a cutoff wavelength of about 600 nanometers. This will transmit our 650 nanometer red light from the laser array, as well as our one other form of infrared light at 808. There's a peak at 808. If you look at the spectrum, and it peters off around 1,000 nanometers. So any infrared light that we get from the system is more likely going to be completely 808 nanometer, which is why we chose this particular camera and filter setup.
Our project uses multiple step-down voltage regulation circuits to step down our 12-volt battery voltage and to power the entire device. Our servos each run on 6.5 volts. They will completely control the arm movement, scoop and deposit our objects. Our MPU, our LiDAR, and our IR receivers require 5 volts, and our microcontroller needs 3.3 volts to operate, as well as our IR laser. When designing the PCBs, we made sure to use large copper pores and ground planes with multiple vias for the heat transfer, and definitely prioritized low switching frequencies for the ICs for noise and reliability.
So here's again another snapshot of our overall schematic. It's just our modulated red laser array with the IR LED for free space optical communication, and then we have our chassis with all three of the optical subsystems as well on there.
So this is our first board. It uses the LM2679 switching regulator. It switches at 260 kilohertz. It's rated for 8.25 watts, and there's a 2 amp fuse on the input, which is definitely overkill for our board, as the ESP won't even draw 1 amp. This next one is the 5.2 volt board. This one will power the Raspberry Pi and the LiDAR mainly. It's also got a low switching frequency of 625K, screw terminal input and output, and a standard 2.54 millimeter header pins. It's rated for 26 watts, and this one has a 5 amp automotive style fuse on the input. And this is the 6.5 volt board with screw terminal input and output. It's 5 amps, which is greater than the stall current of each of our servos, so we should never hit that. Each board is rated for 29 watts. This is the power distribution board. It accepts 12 to 22 gauge wire. This just takes the 12 volts from our battery and puts it out to screw terminals for all of our devices and our motors.
This is the Raspberry Pi / ESP connection board. It uses a single ESP and routes its GPIO pins to the motors on the right and servos on the bottom. In addition, it connects to an IR laser system on the left and an IR receiver on the left and the LiDAR connection on the left. The IR receiver, IR laser, and LiDAR connections connect to the Raspberry Pi connection pins in the center, which is to the left of the ESP32. The ESP32 and the Raspberry ESP32 is powered by can be powered by the USB on the top, or can be powered by the screw terminals on the side above the switches, which control which ones are connected. Unfortunately, we do not have image. This is a photo of the first version of this board. We do not currently have an image of the most recent version of this board, but the most recent version of this board removes the Raspberry Pi power, as it's going to be powered by the 5.2 board directly, and it also now includes a converter to convert 5.2 volts from the USB port to 3 volts to improve communication using USB to UART chip, and to power the Raspberry Pi better. To power the ESP32 better.
So now prototyping and testing. So this is our physical remote development. So this is a PCB that I designed from scratch by myself, with the help from the team, obviously. In addition to the other 7 boards that we have on this project. So to the left, you're going to see the signal that comes from the IR LED, which is a modulated 118 hertz envelope with a signal of 38 kilohertz under the envelope. On the right, you can see what my red laser array of 3 red laser dots modulated at 50 hertz looks like from the third of the 3 timer circuits on this board, and they're all powered by the Energizer battery that we have over there. So great fun. So now for the physical chassis development.
Our first design was drawn out. This informed the dimensions and the material choices. This is where we decided on the macadam wheels and the aluminum construction for the robot.
Yeah, a long time ago.
This is the arm system. It's a 3 degree of freedom system. It uses one 80 kilogram per centimeter servo as the main lifting arm, and then each arm will have a scoop powered by a 40 kilogram servo that moves it in and out to actually scoop under the trash, and then it's deposited above in the basket that we've attached on top of the robot. These are just some pictures during development. Eventually, we thought we could get away with 1 deck, but we ended up having to do 2, and then we actually had a 3rd deck for the basket on top. To the right, we see the 3D printed parts for our camera and our IR light mount.
Yeah.
And here's the completed design with the basket on top, all the electronics installed, and the arms ready for pickup.
So now for software design.
For the software design, we created a state machine with 3 different states: surveillance mode, search mode, and pickup mode. In surveillance mode, the robot will spin around and try to identify a laser light that it sees. When it sees a laser, it'll switch over to search mode and move towards that light. Now that it's seen the light and moves towards it, once you press the button, it'll send an IR pulse to the robot, which will convert it to pickup mode, in which case it will use the LiDAR system to pick up the nearest object in front of it.
This is just a quick overview of our ROS node diagram. This shows how each of the different ROS nodes residing in the Raspberry Pi are communicating with one another. It shows all the connections between all of our peripherals and any sort of interweaving connections that connect the LiDAR unit to our image processor, and ultimately with everything connecting to our navigation package.
So now for administrative content. So as you can see here, this is the distribution of work. So Kobe had his secondary be Griffin. Kobe's responsibilities were leading LiDAR software development, leading imaging processing and image detection, object detection, assisting with the robot chassis and arm prototyping, developing any necessary CAD drawings, and also assisting with embedded development and troubleshooting as a secondary. So Adam, on the other hand, had the job of power system, battery, motor control and regulators, the PCB schematic and design of those regulators, and the ARM servo system construction. Griffin had the responsibility of embedded development and troubleshooting and testing, identifying and developing the drivers for the MPU and MCU, assisting with object recognition and LiDAR software coding as a secondary, and assisting with developing the PCB. So my responsibilities our optical design of the LiDAR and camera, and all of the other fancy LED and laser systems that this project uses. Image processing of the steering system, I helped out a lot with the image processing with Kobe and Griffin to do ROS on these images that the camera was collecting to find the laser dot, and then switch over to my laser system and finding the height, so that we don't pick up objects that are too tall. In addition to that, I did integration of electronic components with optical components, clearly with my PCB design and the timer circuits, as well as design of modulated laser systems. So finally, our budget turned out to be around $1,000, but it's likely more than that with our purchasing of more PCBs and replacement parts for all these things. But yeah, generally that's about $1,000. Thanks for listening. We hope you enjoyed.